All right, class. So welcome back to, really this is still part A, because remember we're dividing this into the parametric unstructured case, which we're doing now, and the structured case, which is really part B. So this is still part A, right? So I'll just write that still part A, although I'll label it when I post these as part B, so hopefully that won't cause too much confusion. But it seemed like a good stopping point to give people a break, so I decided to make it a stopping point. In any case, so remember we just introduced the S procedure, which gives us a way of enforcing conditions like X transpose Fx greater than or equal to 0 for all X such that X transpose Gx greater than or equal to 0. So we are now going to apply this to the quadratic stability condition, which is, remember, if and only if, where we have to enforce this LMI, right? So this will be our F, on X and Q, and here we'll make this this is just Z, like the concatenated thing there. It's just Z. For all, let's call it Z, such that Z transpose something Z now is less than or equal to 0. So this will be our actually negative G matrix, because there's a negative inequality there. So this is our F over here, and this is our G right here. So now we can apply the S procedure, right, to say that here this is our F is actually negative in this case, negativity, for all X and Q, such that X transpose Q, XQ is less than or equal to 0 in this case. Right? Where we moved everything over to the negative sign. So hopefully you understand that if we move it all over to the positive side, it's the same thing. Now I've skipped a step here, I have to admit. And I've actually done something bad, which I tell people not to do, which is have 2 points on your slide. So there's actually 2 sort of important points on this slide. So actually there's 3, right? Because I've skipped a step. I've actually applied the S procedure to the dual of the quadratic stability condition. So there's quadratic stability also has a dual condition where we've replaced A with A transpose, and M with N transpose, and N with M transpose, and Q more or less Q with Q transpose, right? So in the dual system, right, we have A transpose, N transpose, M transpose, Q transpose. So, but it turns out that quadratic stability of that is equivalent to quadratic stability of the original system. So, anyway, I've skipped that introduction because I wanted to get to the LMIs faster, but maybe I should have had a slide for that. But anyway, so quadratic stability of the dual system is equivalent to quadratic stability of the primal. Anyway, so we apply the S procedure to quadratic stability of the dual system. That's what we're doing here. And so here's the F for the dual system, and here's the G for the dual system. And now we have our new variable, mu, here. And we have our old variable P, which is actually a dual variable. Okay. And so this is an LMI condition. It's an LMI condition for quadratic stability of uncertain system with parametric norm-bounded uncertainty. So an LMI. So our first big LMI, right, for parametric norm-bounded uncertainty, and really the first important LMI in this lecture. So this is a real LMI. It's not over a set. It's just an LMI condition. The variables here are P, 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 and the scalar mu. Because remember, M in Q and N are known. Right? And A is known, of course. Right? So that's relatively straightforward. Necessary and sufficient condition for quadratic stability. What's interesting is if you look at this, right? So let's look at this a bit. So here, remember this MQ, right? This looks like something you could apply the Schur complement to, right? Because it's got like a term here, it's got a quadratic term here, and a mu here, right? So it seems like you should be able to apply the Schur complement to this. So let's do that and see what happens. So Schur complement. So these are equivalent, right, by the Schur complement. So what happens when we do that? Well, first of all, it doesn't help us, right, I should say, because remember, mu is a variable, and mu now appears here, and it appears here, right? So this term in particular is nonlinear in mu, right? So that's a bit of a problem. Actually, you can get around that a little bit by taking square root of mu and making, well, it's a bit of a thorn, right? You can move it to square root, which is a little bit better, but it's still nonlinear, right? So this is a problem. So it was linear in mu in the original LMI. So why have we done this, right? Well, not for anything productive, but just more of actually a discussion, right? An important point for implications for unstructured uncertainties, right? So don't use this LMI, I should say. Don't use, because it's not an LMI. Right. In mu. Right. Then why did I do it? Well, because I love applying the Schur complement everywhere, right? Obviously. But no, actually, for a more particular reason, actually, an interesting condition, actually. Which is that if you look at this, right? Remember, this is the format. Remember, this is we had A. This is a dual, obviously. So A and transpose M transpose Q transpose, right? Or we could let's just do the original system, the non-dual. A M N Q, right? This, if we let mu equal 1. This is the KYP lemma. This is the condition of the KYP lemma for mu equal 1, right? So obviously, if it holds for mu equal 1, it holds for some mu, right? Mu equals 1 is a perfectly valid choice for our variable. So in the special case where we said mu equals 1, we get the KYP lemma, right? So what does that say? Well, that says that in the KYP lemma for gamma equal 1, I should say. Right. So it says that if you choose mu equal 1, the condition for quadratic stability is that the H infinity norm of the system, M, is less than 1. So a sufficient condition for quadratic stability is H infinity norm of M is less than 1. Right? That's interesting, right? So my first reaction then is duh, because, right, we know that if right, delta is a matrix, right, and it has norm less than 1 at all time, right, then the H infinity norm of just the matrix is less than 1. And so we're interconnecting a small gain delta with a small gain M, right? And so we already know, right, that this interconnection should be stable, right? So what are we saying here then? Well, we have that quadratic stability, right? We have that if small gain is satisfied, we have quadratic stability, which we already knew. But we actually know a little bit more now, because remember, small gain holds for dynamic uncertainty. And so the question is, do these quadratic stability results, can they also be extended to dynamic uncertainty, right? In particular, if mu is not 1, can you extend this to dynamic uncertainty? Well, unfortunately, the answer is yes and no. So let's move on to the next slide here. So in particular, right, we have that a very interesting result. We have that if the uncertainty is unstructured and dynamic, unstructured uncertainty, meaning that its H infinity norm is less than 1, or it's more generally it satisfies an induced L2 norm, right, condition. But let's do the H infinity because we're all comfortable with it, and let's make that strict, right? So if we have unstructured dynamic uncertainty, then we have this very interesting result, which says that actually the closed loop interconnection is stable if and only if the H infinity norm of M is less than 1, right? Which means that the quadratic stability conditions holds with mu equals 1, right? So that's very interesting, right? It's a little bit harder to prove, right? So we're not going to give a proof of this, obviously. But it says, wow, it says several things. It says the small gain condition is necessary and sufficient for robust stability. I should add the word robust there. It says that, furthermore, the quadratic stability condition is equivalent to robust stability for mu equals 1. Right? Mu equals 2? No. But mu equals 1, yes. Right? So, wow, that's like very interesting. So this says, it's almost too interesting in that, right, there's not much more you can do with it, right? It's sort of like you're done. Right? If you have dynamic unstructured uncertainty, there's a necessary and sufficient condition on M, which for robust stability, which is that the H infinity norm of M is less than 1, right? Necessary and sufficient. If it's not satisfied, there's somewhat destabilizing uncertainty. If it is satisfied, then there isn't, right? So there's not actually much you can do. And we already know how to enforce the H infinity norm is less than 1. So that's interesting. Now the question is, of course, for M mu not equal to 1, right? So when are quadratic and robust stability actually equivalent, right? So this is a very important but very short result on dynamic unstructured uncertainty. Can we say anything more? So this study, this problem has actually been studied in great depth. So the answer is there's not much more you can say, basically. So let's look at it in discrete time. In discrete time, there's this like very nice result with Packard and Doyle studied this very short paper, actually, like 2-3 pages or something like that. They didn't prove much, right? They just outsourced all their proofs to someplace else. But I actually encourage you to read that paper. It's very nice. Andy Packard is a great guy. I visited him at Berkeley a few times. He was really nice. He died from cancer recently, though. So, unfortunately, some of the great people have been dying recently. Jerry Marsden was another of the greats who recently died of cancer. But in any case, so what was I saying? Yes. So basically, this result from Packard and Doyle considers discrete time. And it considers the representation. So actually, we're back to parametric uncertainty. Right. So actually, what they were able to show is that under certain conditions, right, that quadratic stability is equivalent to robust stability. That's limited, right? So basically, quadratic stability is in R. So basically, they're looking at the transfer function here. Right, so you can think of this as a substitute for the system, right? So, so when we're talking about complex valued transfer functions, right? So every value of S. In any case, quadratic stability is equivalent to robust stability in this case of unstructured dynamic uncertainty. So it's a very nice result, Packard and Doyle. In our case, however, again, unstructured dynamic uncertainty is somewhat less interesting because, right, small gain is necessary and sufficient. So there's not much more we can say about it. So let's turn then back to parametric uncertainty. So not dynamic uncertainty. Yep, yeah, I didn't want to do that actually. So obviously I wrote the condition for the LMI for quadratic stability in terms of the dual system because I wanted to do controller synthesis, obviously. I didn't want to devote another slide to getting the dual version. Right, so it's relatively easy. So now we're going to add those exogenous inputs and outputs. So we've got the LFT again. There's our delta. Now we've got M here, but it's got some exogenous inputs. I think this is our U, and here we're doing state feedback. Actually, there's no exogenous inputs in this. That's the next slide. Sorry. So we're doing state feedback. Y equals X, and we have a K matrix which determines our U, and then we also have our P's and Q's. Mind our P's and Q's. Right. So again, the state space system representation, normal I don't know why I have a not there. That shouldn't be there. Plus an input term from our controller, plus the effect of our uncertainty, which is determined by a parametric, right? Parametric and norm-bounded uncertainty. So norm-bounded goes there. And the thing going to our norm-bounded uncertainty, right, is the same as before, nx plus qq, right, the direct feed-through term there. And then, of course, we also have something from the input that goes to the uncertainty as well. Right, so several terms there. So if we apply now a controller, right, we choose u equals right, kx there, right? We apply that. Then, of course, right, we just substitute a for a plus bk. This becomes n plus d12k, right, in there. And we can, like, ignore these two terms. Okay. And then we just apply the LMI for quadratic stability, which is necessary and sufficient for quadratic stability. And we get an LMI in terms of three variables now, p, k, pk, pk, kp, and mu, right? So three variables there. Now, of course, we have three variables, and this is linear, so no problems there. But these two terms are bilinear, right? So, but they're bilinear in a very comfortable and familiar manner. In particular, we can use the variable substitution, z equals kp. Replace that with z. Replace this with z. Replace this with z transpose. And we get an LMI in p and in z. Right. So we can apply that to the next slide. All right, this is an LMI in z and p and z and mu. Right, those are our variables. Mu, z, and p. So identical to the stabilizing state feedback controller synthesis problem we had in lecture, I want to say 9, something like that. I don't know. No, maybe somewhere around. No, not 9. That was the optimal one, so probably about 6, maybe lecture 6. Anyway, we've seen this before. We'll see it again. It's nothing new. So this is an LMI for quadratic stabilization. Quadratic stabilization. Using, I should say here, state feedback. U equals kx. So assuming we output all the states. We don't have one for dynamic output feedback, unfortunately. So, okay, an LMI for, again, right, quadratic stabilization using state feedback with parametric norm-bounded uncertainties. You see where we get so many different varieties of LMIs in these, right? I mean, so many specializations, right? Quadratic stability, state feedback, parametric uncertainty, norm-bounded uncertainty. And, right, you could change any of those words and you get a different LMI. And actually, you can change most of those words, and I've given you a different LMI, right? So obviously we can now apply, I think it was lecture 9 or something like that, and we can get the state feedback H infinity optimal quadratically stabilizing LMIs. So this is, I say it's H infinity, right? It's H infinity optimal, quadratically stabilizing. Now state feedback. Didn't include that because it would have like wrapped the line. Parametric, norm-bounded uncertainty. Now let's parse these words a little bit. So first of all, quadratically stabilizing, right? There's no such thing as quadratic stabilization, right? So this just means it's conservative, right? Where it means we're using a single Lyapunov function to prove all of these for all deltas. So when we say quadratically stabilizing, we just mean we're using a single Lyapunov function. Parametric norm-bounded, we've covered that to death. State feedback, we know what that means. Let's parse this H infinity thing here, however. Because actually, H infinity is misleading. Right. So specifically, what we mean by that is actually that if the LMI is satisfied and we define our exogenous input as W, right? So delta M, and we have an exogenous input and an exogenous output Z, right? Then the norm of Z, and here I've actually labeled it Y, and then it is less than gamma times the norm of W. And here I've actually labeled it U, so that's a mistake. Right, so again, right, if you and this is a more serious mistake. So if you implement this controller, the state feedback controller, then even if delta is time varying, right, and you have no idea what delta is otherwise than that, but it satisfies some norm bound, then the size of the exogenous or the regulated output is going to be less than gamma times the size of the exogenous input, right? So this is our conclusion, right? Does that mean that the closed loop system has H infinity norm less than gamma? So closed loop system have H infinity norm less than gamma? No, because it's a time varying system. There's no such thing as a transfer function for these systems, and there's no such thing as a transfer function for these systems. And so we can't define the H infinity norm. So this is misleading, right? What we really mean is this condition, right, is satisfied. Okay. So all right. At least now I've that's what we've parsed all the words, right? H infinity is wrong, it's misleading. It's actually an L2 induced norm gain bound. Quadratically stabilizing is also sort of weird because actually it just means it's conservative and we use a common quadratically Lyapunov function. State feedback, I didn't mention it, so I guess that's misleading. Parametric norm-bounded uncertainty, that's right on the dot though. In any case, right, so what's the LMI? You can more or less guess what the LMI is, but it's a combination of the KYP lemma and the S procedure. The only tricky bit here is that, so the tricky bit is we had to set Q equals 0. So no direct feed-through term. And why did we have to do that? Well, that's because if you remember, Q shows up, it shows up here, and here, and here. And that's a bit annoying because that makes gamma show up everywhere as well. I mean mu, it makes mu show up there as well, and there and there. And that apparently causes some problems. So we had to get rid of Q there. So that's not too bad, right? It's often the case that the uncertainty doesn't feed back directly into itself. That's the Q term here, right? So it's not that bad, but you know, it's kind of a disappointment. But in any case, if you make that assumption, you can combine the KYP lemma with the S procedure to get an LMI for H infinity optimal, whatever that means, quadratically stabilizing, whatever that means, state feedback, parametric norm bounded uncertainty. And actually, this LMI is straight from Boyd. Actually, he doesn't have a proof in there. I think I worked through it at some point, and it actually comes from application of a Finzer's lemma, or a variation of Finzer's lemma. So if you want to see the variation of Finzer's lemma, you could actually go to Z 1992, or you can look at Caverly's notes. It's in there as well. So remember, that's one of the things on Canvas, so you can download that. And basically, it allows you to eliminate uncertainty. So it's a variation on the S procedure where we can say that this inequality is satisfied for all delta less than 1, if and only if there exists an epsilon and epsilon inverse, epsilon such that this inequality is satisfied. So similar to the S procedure, but not exactly. Yeah, but unfortunately, of course, the use of this requires us to eliminate that Q term, which is not this Q term, right? That's not equal to each other. Different Q term, right? This is a general form of Finzler's lemma here. Okay, so basically, what have we done now? We've considered the case of norm-bounded parametric uncertainty, but in the unstructured case. So we're going to stop now, and when we come back, we're going to consider the case of structured uncertainty. So that's where we know a little bit. We know that the uncertainty still has a norm bound, right? So it's still norm bounded. But we know a little bit more about it, specifically, typically, that it's block diagonal, right? And And block diagonal structure tells us a little bit more about the relationships between the inputs and the outputs. And if we can take advantage of that information, then we can say a little bit more about, we can give less conservative conditions, more accurate conditions. But anyway, we'll do that when we come back. Right now, we'll just stop the recording and come back later.